And we are just about ready to get going. Everybody, I am Peter Fisk, and as many of you heard, I am now the Emeritus Executive Director of NAWI. As of Monday, we have Dr. Kevin Warner, who's joined NAWI as the new Executive Director, and I am stepping into a role called Engagement and Technology Transitions Manager. And one of the greatest things about that transition is I get to focus on things like this, NAWI's webinar series, and our engagement with the larger water community. So everybody, welcome and join us today. Uh, let's move on to the next slide. So a little housekeeping. We are recording this, so don't worry if your friends aren't here. And if you want to catch some notes, you can always get slides after the fact. I noticed we're a little laggy on the slide transitions. No problem. But we have everybody in the audience muted during the presentation, but I emphasize that at any point you just put a question into the chat. So here's the chat. Chat us up. And then as we get to through the sessions, we can then go through your questions. Another thing I would suggest is everybody has a little video thumbnail. I'm just going to suggest that everybody rename themselves. You know how to do that? Go up to your video thumbnail to the three little dot box, and you click open that box and you go down to rename and just put your affiliation. So I just changed my affiliation to NAWI. And that means everybody can know where everybody's coming from. Again, you just hover your cursor over your video, and then you'll see a little triple dot appear, and then you can click that triple dot, go down to rename. Oh, I only can rename hosts. Sorry, everybody. But oh well, I thought it was a good idea. But anyway, let's keep going. If you have audio issues, it happens from time to time. All I can say is we not much we can do, but you've got a recording, and that helps a lot. Next slide, please. Okay, so as we move on, remembering everybody that NAWI is a national program, and the Department of Energy credits us for the time you spend with us. So for all of you out in the listening audience, we can allow the hour that you're spending with us to count as cost share to the NAWI program. So after the session, please go to this reporting form, this smart sheet, and just fill it out and tell us the hour that you spent with us, and we can credit that hour towards NAWI's overall financing and cost share goals. Lastly, if you are not already following us on LinkedIn, LinkedIn is now one of the major ways in which we will send information out. The other way is on the NAWI website at www.nawihub.org. You can go press the join button if you're not already a member. That'll just give you access to all of our communications, and we'll add you to our mailing list, et cetera, et cetera. So with that, I'm about ready to introduce our three speakers today. And Ryan, why don't you go and put the first slide back up, if you don't mind, the title slide. Because one of the things that we're doing, obviously, as everybody knows here, now he's been renewed for another 5 years. And one of the areas of research that we are focusing on is what we call premise scale water reuse. The idea that in addition to a large centralized water system, we can envision a world where we also have small scale systems operating locally, even down to the scale of individual buildings, and taking water that has been used in one application that we used to call wastewater, but purifying it and converting it back to something that we could use in another application. So this is a very exciting area of kind of research and technology development opportunity, and it will be an area in which NAWI is making research investments in 2026 and beyond. So, as many of you know, the NAWI program, one of the principal modalities of NAWI's program is we are doing research in the form of piloting advanced systems, piloting systems in actual working environments. And so as researchers, many of you understand that one of the key challenges is, where can I find an environment that is, first of all, interested in having my research project operate, and secondly, can be a good collaborative partner as we demonstrate some of this advanced technology together. That's when I learned about the extraordinary team at the University of California. As you know, University of California has 10 campuses, 6 medical centers. Thank you, Ryan. Um, and it's the largest public university in the world. And one of the key advantages that the University of California has is with these different campuses, each campus has a team of facilities managers. And a number of these campuses are also very forward leaning on sustainability projects. So, in today's webinar, I wanted to introduce the NAWI community to 3 of these sustainability managers at 3 different campuses in the UC system. And in particular, this team who you'll hear from today have had some experience developing and deploying water reuse technologies on their campuses. So I thought that it would be really great for us to hear from each of them and hear about how they have approached some of these projects, what some of their priorities are, and for you, the research community, to understand how you might be able to partner with some of these campuses with ideas that you might have for advanced water reuse technologies that would be part of the NAWI program. Eli Perchek is the Conservation Program Manager for Energy and Water in University of California, San Francisco, UCSF. And Eli is going to start us off by talking about some of the projects that UCSF has pursued in the area of water reuse and also water storage. As many of you know, San Francisco is a peninsula. It actually was an arid peninsula. San Francisco burned down 3 times until they were able to acquire water from the Sierra Nevada across the Central Valley. So San Francisco UCSF, in addition to very forward-thinking operational mindset, also has a practical mindset of living in a seismically active area and understanding how this campus and this diverse set of facilities might be more self-sustaining in times of emergency. Alex Yazbek is a civil engineer with physical planning, development, and operations at UC Santa Cruz. Go Banana Slugs. He has worked on a broad range of civil engineering issues and will talk to us about some of the areas of deployment that UC Santa Cruz has done. And finally, Jeff Eisert is at UC San Diego, and he focuses on a wide variety of projects, including public facility sanitation, temporary facility sanitation, and construction plan review, et cetera, et cetera. And Jeff's going to wrap up our discussion. So I ask each, Eli, Alex, and Jeff, to tell us a little bit about their campuses, tell us a little bit about their water reuse projects historically, as well as some of their ideas and visions for where water reuse might fit in. And I'm going to invite Eli to start. And so we will relinquish the talking stick. And Eli, thank you so much for coming. And we look forward to hearing about UCSF.
Thank you so much, Peter. I will get right into it. Share my presentation. Okay. UC San Francisco water recycling. Just for context, UC San Francisco has 2 main campuses, older campus at Parnassus, newer campus at Mission Bay. We're the only UC dedicated to health science research, so our buildings typically are filled with laboratories. We have a lot of satellite facilities and clinics throughout the Bay Area, and administratively, we're separated into campus and medical center hospitals. And as Peter was alluding to, all the UC campuses are self-permitting under the state of California. We each have a building permit official and fire marshal. Here's our current water recycling that we do at the Parnassus Central Plant. It's been in place about 15 years. So we produce reverse osmosis purified water for the researchers, and then the reject goes to a storage tank and then gets used as makeup water for the central plant cooling towers. This is an example of a study at our largest research building, Genentech Hall, where we looked at using RO reject, stormwater, air conditioning condensate, and using it for cooling tower makeup, vivarium quenching, and irrigation. It didn't happen because it was just too expensive. So this is just an example of a retrofit on an existing building. Even if the supply and demands match up, it's just an expensive undertaking. And in San Francisco in particular, because we're really cool climate, we have low air conditioning condensate. So I'm going to go over a study, a water recycling study we're doing right now, and get into details on UCSF Parnassus. So Parnassus is located on Mount Sutro, which is in the middle of San Francisco. And then you can see the boundary of the campus. There's a central campus core and then a large mountain reserve. To explain, San Francisco has a combined storm and sewer system because it's old, and this results in when there's big rainstorms. Basically, the city has sewage overflows at the beach areas and in some of the neighborhoods. So we're supposed to manage our peak flows on our campus sites. The project I'm going to go over, it's the top of the channel watershed, which you can see in this map. So we're building a new hospital, a very large 1,000,000 square foot hospital at our Parnassus site. And the project includes the conversion of single-walled diesel fuel tanks, which in California we have to decommission, and converting those into stormwater detention tanks. So 4 30,000-gallon tanks for a total of 120,000 gallons. So the scope is just stormwater detention. There was no water recycling scope. So we've been looking at how can we recycle the water. And just for you, so you can see, this is the drainage area. So there's the campus. There's a building just north of the drainage area. That's an elevated building. Just to explain, it's called the Dolby Building. And there's a roadway that goes up the mountain that drains down to these stormwater tanks. And the red outline is the new hospital. We've been looking at this in a variety of ways for about 4 years. So initially, we looked at constructing above ground tanks under the Dolby Building. And it was just too expensive because we would have to seismically reinforce the slab. Then we looked at using these planned stormwater tanks for central plant cooling towers and irrigation. And while there's demand in the wintertime, the issue is just the supply didn't match up well enough with the demand to make it worthwhile. Then we looked at, could we use this for steam boiler makeup at our central plant? We have a cogeneration facility there. The issue is that some of the steam has old distribution to the hospital. And in California, you cannot have any recycled water in a hospital. So that nixed that concept. And then we got to where we are now, which is at 2 of our laboratory buildings to use the proposed recycled water for industrial process water in the laboratories. So, this is pretty, I guess we hadn't considered this at first because it's kind of dealing with all the researchers in their labs, and this is the water that they're using for the research. So it's much more complicated than just, using it at the central plant. And basically the researchers, all of their laboratory water is this industrial water. So that's the lab faucets, ice machines, autoclaves, glass washers, cold rooms. Those are the uses. So we're looking at this through following California Title 22 and the ANSI ST79 standard. It's a standard for water used for sterile process. And they're pretty close in the level of water treatment that's required. And we're looking at several catchment scenarios. So the original catchment scenario plus the Dolby roof as an option. And then the pink area, there's a parking lot called the surge lot at the bottom. And part of this study is considering, in addition to the catchment, putting storage tanks in the surge parking lot. This is just the detail of where the water treatment equipment would be next to the stormwater tanks, and then distributed to the industrial water risers. These buildings are about 16 stories each. And this is just so you can see how much rainfall we think that we would get into these storage tanks under several different scenarios: a drought year, average year, and then a wet year. So as I mentioned, the city is very interested in how we're managing peak flows. So this analysis includes, how much volume of peak flows that we would be reducing. Under the scenario, we're using the original tanks, and then also if we were to add water storage tanks in the surge parking lot. So finally, this study should be done in the next month. It looks like it would cost about $2 million without the additional storage tanks. We have expensive water, as you can see, but potentially this project could have about a 12-year payback based on like an average rain year. The money would come from UC bond financing which is typically used for energy saving projects, but it could be also used for water saving projects as long as we're saving utility costs. So we have some things we need to figure out: cost benefit of the surge lot tanks, any issues with adding the Dolby roof collection area, and then we need to finalize what are the peak flow reduction. Talk to the city about that, and then the only way this project will get financing is if it has a good ROI, which previous project studies did not get us a good ROI. So, and just another issue is that the storm drainage uphill from the project is almost 100 years old. So it would be like another project to get that storm drainage replaced. And that's my presentation.
Great. Thank you, Eli. I'm putting in questions in the chat, everybody. You can do the same thing, but we're going to circle back at the end. I want to get through everybody's talks first.
Thank you.
But Eli, thank you so much. Alex, what's going on with the slugs?
All right, let me get my screen set up. Peter, is that in presentation mode?
It is beautiful. Thank you.
Okay, great. So thanks, Eli. So I'm Alex. I'm at UCSC. I'm a civil engineer, and I'm going to talk about our stormwater to toilet flushing project at Kresge College. So the context is this is a new residential development at one of our colleges, Kresge College. And for those of you not familiar with California, we have post-construction stormwater requirements, and that means that we have very strict rules about how we need to deal with stormwater for every project we do on campus. So that means we have to retain a lot of water, we have to detain a lot of water. If you want to ask me about that later, I can go over the difference between those two things. So the stormwater requirements really place a lot of restrictions on a project. And so the stormwater is where this begins. We've collected a lot of stormwater. What do we do with it? Another thing to know about UC Santa Cruz is that we have very complex geology. We are a karst topography, and what that means is the rocks underlying our campus are limestone and marble. These are two rocks that dissolve in rainwater. So we end up with a lot of sinkholes, underground channels, bizarre underground cavities, all kinds of interesting things on campus. So we have immense challenges with building and really complicated challenges when it comes to managing stormwater. And we're the slugs, where we want to be innovative. We want to show that we're innovative with water reuse. We want to be sustainable. So we have a lot of, all these great ideas, concepts, intentions. We want to be green, sustainable. Students are just happy. Santa Cruz loves it. Everyone's happy. And if that was all there was to say about this, that would be my only slide. And I'd say, we're green, we're good to go. End of discussion. But unfortunately, there are a whole lot of lessons to be learned from this project where we put in a water recycling to toilet flushing system at this college. So the design that we have is to treat 500,000 gallons per year. And the system is very simple. Stormwater collection. So it's not just roof runoff. Some of the water is on the ground before it goes into the underground cisterns. Then this water gets pumped through a treatment system. The treatment system is about as simple as it can be. It's a multimedia filter, and then there's UV disinfection, and then there's a pump to pump it up to a dual plumbing system in the building for toilet flushing. There is no residual disinfection. and there's no turbidity monitoring. And I called out those two things because if anyone here is in the business of designing water recycling systems, I'm sure you're going to have questions from me on that. Okay, so now we actually get to the reality of what's happened with the system. So we've had, just on this portion of the project, about $2.5 million in change orders. And that does include change orders to the stormwater system. So it's hard to separate what the costs are for stormwater versus what the costs are for the reuse. But one thing that we can focus on is the project cost is $400,000 per bed. So I'm glad Eli started with a hospital because the only thing more expensive than building housing at UC Santa Cruz is to build a medical facility. We have the highest costs per bed across the entire UC system. And it's difficult to kind of untangle and really analyze why that is. A lot of it has to do with that karst topography I mentioned, the complexity of building on campus. But again, that cost to me is outrageous, and it is a huge hurdle we need to somehow start unraveling and solving as we move forward. And I bring it up because, again, something like a water reuse system is often an additional requirement on a project. And again, I need to ask the question, is this really something we need? And on top of all of this, this project took beneficial occupancy about 2 years ago. The system is offline. There's been pump sizing issues. We still don't know just how well the system works, what it takes to operate it, what are the other issues we're going to face, what are the other costs we're going to face. We just don't know because it is yet to come online. And so now we start looking at what is the value? What's the value of water? So if we were to buy this 500,000 gallons of water per year from the city of Santa Cruz, roughly $13,000. That's the annual value of the water displaced by this treatment system. So something interesting here, just as a comparison, Eli's looking at 14,000 gallons per day. We're looking at 500,000 gallons per year. I think it's quite a big difference in sort of size and scale of these two systems. Another alternative is we do not use groundwater on campus, but we could. We have a well on campus. It's capable of producing about 75 million gallons per year with insignificant impacts on the aquifer, and it's currently offline. It's offline for political reasons. It's offline because there's a fear of the city of Santa Cruz suing the campus, of residents in the city suing the campus. So there's a lot of political reasons why we don't use this groundwater on campus. And so total campus water usage is 160 million gallons per year. So we could produce roughly half of that through groundwater. We have this huge aquifer under the campus. So really the question for me is there a scale where reuse makes sense? And what does that look like on campus? And how could we integrate all of these reuse systems together so that we're making it make sense? So something else to think about for folks not from California, we only get rain realistically November, December, January, February. We do get a little bit in October, a little bit in March, April, but typically we only have 4 months where it's raining. So we can only use this toilet flushing system for about 4 months of the year. And then what happens in drought years when it's not raining? What else do we do? And so we're starting to talk about how do we integrate the system with our cooling towers, with a plant to take wastewater from the sewer and treat it. What are the other ways we can connect everything together to have it make sense? And there's the regulatory context. We don't know. We typically a system like this would have a licensed operator to operate the system. We don't have any licensed operators on campus. Our plumbing staff could probably keep the system running, but we still don't know. As the regulations change, again, we are part of the UC. We get to decide whether unlikely that the state regulations will apply to us. But again, we don't have any continuous turbidity monitoring on the system. We don't know if we need to take daily grab samples. And again, what scale does this make sense? If we are required to do this, how big does a system need to be to justify the the cost of an operator, the cost of all this sampling and monitoring? And I've included the proposed pathogen log reduction targets that California Title 22, the water code is, oh sorry, Title 24 is planning on implementing. And for those of you familiar with treatment system design, you can see that these log reductions are very high. Used to be that just if you took surface water out of a river, you would need to achieve roughly, 4 log reduction in viruses, 4 log or 3 log reduction in Giardia, and I think 4 log reduction in Cryptosporidium. So that's just a comparison. The requirements for reuse are going to be much higher than they have been in the past. So lessons learned. I would say lead with common sense. It feels like on this project there was a cascade of bad decisions. Decisions with pumps, decisions with including this project, decisions around stormwater management. It just seems like if you don't have a good understanding of what's possible in the beginning, bad things can or complicated things can end up happening. Lead with value cost analysis. I think this is critical. There's sort of a mantra system, and that is it's the right thing to do. And every time you say, oh, but what about the cost benefit of the system? People will immediately answer, but it's the right thing to do. And I don't agree with that. I think the right thing to do is something that makes financial sense as well. I think we need to start including that in our sustainability decisions because I look at the money that's been spent on this project and I think, hey, we could have brought our well online, run groundwater to our farm, to our arboretum, to our fields with that money instead. And that would lead to savings of roughly $750,000 a year had we done that. But instead, we spent that money on this recycle system that's gone unused for 2 years. I think we need to create good standards. Our designers need help. That's something I'm surprised by, but it seems evident that we ended up with a design team that didn't really know what they were doing. And again, think about the scale. Does this make sense? How big does the system need to be for it to really be the right decision for whatever it is? I'm concerned about future regulations as those become more stringent. What are the knock-on costs that we as a campus have to face? So again, considering the monitoring, the operation, the maintenance from the very beginning, often that's ignored. And my personal thing is less is more. Things break. This system is about as simple as it can be, and it's not running because there's issues with pumps, there's issues with flow restrictors. We're struggling to get the design team to come back and fix the system. So the alternative to this is perhaps a packaged plant would have been better, that it's something that arrives in a box, we plug it in, it works. If it doesn't, we send it back to whoever sent it to us. Maybe that's a better way to do it. And then my personal push is to design with nature. More gravity, more groundwater, more composting toilets, urine diversion, infiltration. I don't know where this could go, but somehow we're still very much in this concept of using a lot of equipment, a lot of pumps, a lot of traditional things. And I'm just wondering what else we could be doing. What would it look like if we were to take a low energy, low cost approach to all of this, and how different would that be? So I'll leave it there. I don't think I have anything else to say. Uh, I will
Great.
say that thing I will say, Eli, your cost of $30 per 100 cubic feet, we use roughly $20 per 100 cubic feet. So our water is slightly cheaper than San Francisco. If our water were slightly more expensive, the system might have a slightly better payoff. So I'll just leave it with that. And that's it.
Great, Alex. Thank you so much. All right, bringing up the end, Jeff, tell us what's going on down south.
All right, let's see. Hello, everybody. Let me share my screen with you guys. Okay. You guys see it?
It's coming.
Okay. All right, you see the
There we
slides
go. It's
there?
in presenter mode.
Okay, yep. Does that work?
No, it's presenter mode, so we see both you and the next slide.
Oh, I see.
So, I think you go to display settings at the top.
Display settings.
Swap.
Yep. Did that do it?
Try again. Display settings, and I think the first thing is swap, presenter, and slideshow.
Okay. Well, let me just go with what I got.
That's fine.
Is that okay? All
That's
right.
fine.
Okay. Welcome. Thank you. I work at UC San Diego. I oversee the recycled water program and the gray water. I also do the health inspections for campus. So I kind of come from a little bit of a different element, but my angle is a lot of the health and safety aspects of it. So at UCSD, I've been here 18 years. And we've experimented with the gray water systems here too. We have about 15 years of working through different systems. And currently we have about 5 or 6 gray water systems. But let me give you an intro of where we're at. We're the beautiful campus down here in San Diego. We have Scripps La Jolla right down by the beach. So we have a very coastal Mediterranean environment. Campus is down here. We have the main campus, we have SIO, and then we also have a medical center with us. We're all kind of locked together. We have a great school of engineering, so we're very science-based, so that kind of helps. The outline I have today, I just want to talk about a little bit of recycled water, cooling towers, our gray water systems, lessons learned, and a little bit about this really innovative stuff that's happening with the city of San Diego and the Pure Water Project. So, because I think, in my opinion, what I see is kind of a quantum shift in recycled water, kind of changing in the future because of certain reasons, and it's kind of starting here in San Diego. So just sort of a little background, we got our feet wet using the recycled water from the city, like in around 1995. The city said, hey, I think we had Governor Schwarzenegger at the time, and he said, hey, let's divert some of this treated sewage, start using it for the golf courses and all that. Also here in San Diego, the pharmaceutical industry, they all huddle around where the purple pipe is because they have cooling towers too. They have very cold refrigerators. So in an interesting way, the history of San Diego relates in our pharmaceutical industry like Pfizer, Biogen, Illumina, they all are here because of that recycled water 15, 20 years ago was a very cost-effective, low-cost product that they could utilize. And then so we've all utilized that. So I go through the headaches of dealing with submitting all the irrigation samples, the cooling sample or plans to the county and city. I deal with those crazy agencies. And then I'm in communication with the main plant that's over down in San Diego to our east. So we have also a distribution system here on campus. So which was really nice is over the years, we've built out a 12-inch C900 loop system of recycled water that goes through various vaults. And it goes around the campus, and then it stubs up and goes to the irrigation, and then stubs up and goes to our cooling towers. So big main, we created our own little recycled water sign, big meters that we have from the city. So I work with energy and sustainability to see our bills. One interesting thing is our water bills go from 500K to 900K a month. So we gobble up a lot of water. And so in an interesting way, although we utilize a lot of recycled water, it's still a small, maybe 15, 20% piece of the pie of our total potable consumption. And so we do a lot of effort for the recycled water, and it looks in gallons wise like we utilize a lot of recycled, but per our profile, it's still a small percentage, and gray water even smaller. So we oversee the installation of the piping. So there's a lot of regulations with the purple pipe, cross connections. And then we get into the gray water. So we started doing this kind of like Alex and Eli mentioned, is that the UCs were in charge of our own plumbing code. So that really gives us an advantage to say, okay, let's kind of step out of the bounds of design and design something and permit it ourselves. And that's where they kind of roped me into this, and I didn't really know much about it. But then you have to then start looking at the health and safety hazards of what you're designing if you're going out to that leading edge. So that's where you want to have a look at the bacteria, the Legionella, and I watch over like the water management plans for the hospital. So there's a nice tie-in, and that's what you kind of see with like the California state regulations with gray water. It relates to like UV treatment and bacteria. So you have a design engineering aspect, and then you have a health and safety aspect. And things like UV light, if you put that in there as a standard, those UV lights they expire after a couple of years. So then you're gonna have to replace that if you want to get those like say 5 or 10 log reductions of bacteria. But in regards to our gray water, what we've learned, we had The Killing building was a great example of a LEED Platinum building that we had a lessons learned. We didn't really know what the water was coming down from the student showers. And we were like, well, what's it gonna be? I thought it was gonna be something more like, almost like a swimming pool, where it's like a Staph aureus bacteria, some funk on your skin, down into the tank, and then we treat it and put it onto the irrigation. Well, the water didn't turn out like that at all. It turned out to have a lot of hair and sand in it, but not funky. And it didn't smell bad, but the design that we had of the treatment down in the mechanical room were almost like these coffee filter socks. And so the first thing that happened was the sand and hair went right into these sock filters and jammed the whole thing up. And then the water was supposed to flow through. Nope. So then housing had to utilize all their maintenance staff to keep cleaning these filters. And we're like, oh my gosh. So it was really, but we didn't know. I remember when we did this, I was like, I don't know what the quality of the water is coming from the student showers. We're like, let's capture the shower water, let's treat it, put it out to the irrigation. And so it turned out that we ended up just building a diversion pipe right around the whole treatment system, and it went straight to the sewer. And so although it was a LEED Platinum building, it was a grandstanding ovation. That treatment element was really important. But I remember even when we designed this thing 10, 12 years ago, kind of saying, well, where is the knowledge out there about how to do the treatment per your water? And it wasn't really out there. Later, I found an engineer that said, yeah, if you did this sort of like drum spinning design that they do in Australia, they've kind of figured it out, that would have worked. And I was like, oh. So it's about really finding that technology per your water. So that was an interesting sort of lessons learned. So now we've kind of built out a few more condensate recoveries. Since we're by the beach, we have a high humidity and we have a lot of laboratories. So we're already drying out the buildings with the air handler units. So we've designed it where we intercept the floor sinks where the HVAC units discharge. We run it to a large tank, put it through a little treatment, and then either inject it out to the irrigation, or what we started to try to do is inject into our 12-inch recycled water main line that's on campus. And so in going through the gray water, so we have systems like this. Here's like a holding tank. This is an example. This is Waterworks, was one of our leading designers. So one thing that was kind of funny that happened before we started getting gray water is San Diego already had pharmaceuticals and beer. And that was sort of like one of our big lifestyle economies. And so this guy, James Wallace, that I met, he worked and started Waterworks, and he understood all the treatment trains, how to treat water for pharmaceutical production, how to treat processed water from pharmacies, and then how to treat city water to make it clean for the breweries. So he could design one of these whole skits for us of how we needed to treat. So an example is like we'd add some O2 to this tank to kind of keep it from getting funky. And then he would have these pumps to overcome the pressure as we inject it out. And then there's a UV element from Equova down here. One of the other elements that we learned was, since we had recycled water from the city, in the California Plumbing Code, it wanted to really call a dual plumb building recycled water also. And so we said, no, we want that to be completely different. We want to call it something else. So one of the things we came up with is our own labeling of the piping inside for these gray water systems. And what we came up with is label the piping what the source water is in a purple label with white lettering that's very standard, but label it for what the source is and then label it post-treatment. So we would have a label such as recovered condensate or RO discharge. And then after it goes through treatment, you would say something like condensate water. That way, this is kind of coming from my perspective in health and safety, is that when you have the facilities guys up in those buildings, you know where the hazard is. So RO condensate is pretty much salty, but the condensate water could have bacteria in it. It could have Legionella. So that's where we came up with that. But that was to differentiate that we don't have what's called a dual plumb system under the recycled water guidelines, which is Title 17 and 22. So that was an interesting thing, but I had to sort of work with the designers to get this in there. And one thing we learned too was that our gray water condensate production peaks when the humidity peaks. So summertime, when you're drying out the buildings, it makes sense, but you still get a lot of production in the wintertime too. So what we ran across with one of ours was, what do you do with all this water in the summer when out here the plants are dry and hibernating? Like, we don't have rain in the summertime. We get all our rain in the springtime and early winter. So we ended up with a capacity, and one of our places, the Biomed 2, we just would treat all this gray water and then it'd go straight into the sewer. We're like, that's beautiful water. But the intention was to put it out into the grass, into the landscape. But it turned out that the landscape didn't want it, but we weren't sure about this bell curve. We didn't know if it was going to be flat or if it was going to be undulating. But it turns out that it produces when we have the highest humidity, which is the summertime out here. And what that relates to then, the tie-in that we found out, is that the gray water systems for us work really well with cooling towers, because we have cooling towers at various areas on campus. They run on recycled water. And when do they use the most water for cooling? The summertime. So our gray water production on our cooling towers are like a match made in heaven. The plants don't want it, but the cooling towers do. So then we designed a couple systems where they injected into the purple pipe that went through campus and went off to the cooling tower. And the nice thing about it is that the quality of this condensate is really clean and it's cold. So when it goes into that purple pipe, it's actually reducing the likelihood of Legionella and Cryptosporidium growth, and it's actually diluting out some of the salts in that water. But no one's really done this before, and so we got our hands slapped by the county and the city when they finally said, you cannot inject into this purple pipe anymore. No one's done this as a capacity thing because that's a regulated pipe. So we had to start to do it to figure out what the production curve was. But then in the end, the regulators came and said, nope, you're not going to do this anymore. And so now we're kind of like, we've had to disconnect those systems. The city could have approved it if they wanted to. So during COVID, I brought the city public works out and I said, hey, use me as like a laboratory, use me as an experiment. You know, I'll test the water, I'll give you lab reports as it is. They were almost open to the idea because they could have regulated me, but it would have took more manpower for them to review my plans. And so one of the lessons learned is that when you get into these sustainability elements, you're going to butt up against either regulations or regulators, and they're obviously risk adverse. So it's a couple steps forward and sometimes a couple steps back. And then that's it for most of the gray water stuff. So right now we're kind of at a maximum because it's a smaller bump in our overall water usage portfolio. So it doesn't have a big dent. But I just wanted to talk a little bit about the pure water. And what that is the city of San Diego is investing $4 billion to basically take recycled water, put it through RO filters and turn it into drinking water. So it's direct potable reuse that they're intending to do. It's a big deal. We tried it a long time ago, but it didn't work because the city's taken on a big risk. You're taking this source water, treating it, and then providing drinking water to 3 million people. So obviously, if 3 million people start getting cancer and illnesses, the city's on the hook. So their liability is very high because no other treatment facility in America has done this. But what they're doing is, since we're down at the southern portion of the state, we don't want to buy water from LA DWP anymore because it's expensive. So rather than discharging the recycled water, we want to treat it, turn it into potable. Then when you put it through these RO filters, you can sell it at a higher cost. And that's great. What it did was the city cut us off from any new recycled water projects, which was good for me because I was already buried in work. But in the bigger picture, what's coming forth is that the recycled water, being a cheap product that used to just get discharged to grass, irrigation, and whatnot, industrial uses, is now going to become a little more expensive. That water droplet that used to be throwaway is now, especially in San Diego, valuable. And so if you have these RO filters already in place and the cost of those filters and the PSI for those pumps is going down, then that recycled water is better served becoming filtered and turned into a drinking water droplet. And so this idea that sort of Arnold Schwarzenegger put in of, hey, instead of discharging the treated sewage to the ocean, let's turn it into recycled water. It's now kind of going through the next phase where it's not cheap anymore. It's basically an unsubsidized marketable commodity, and that water drop was expensive because of the distance it has to travel. So San Diego's unique for that because we're at the bottom of the pipe, basically, for all the water from the mountains in the Colorado. So this is where we're kind of pushing the level of technology with the filtration systems. And so the other element is all the inspections that come with recycled water. And so the counties and cities understand it. It's heavy in regulations, and the state isn't really helping. So this pure water can basically then take the recycled water, treat it to a level where it's not hazardous, it's not considered treated sewage, sort of under the EPA, and make it almost a low-level potable, distribute it still through the purple pipe, charge more for it, but then it doesn't require all the testing. So it's a sort of a different level. So the idea the city has then is that you have a nice polished drinking water quality that you charge, say, $4 for. The recycled water then goes from being a cheap product with lots of chemicals, scaling and whatnot, to a slightly more expensive item, but doesn't require testing and it has a better quality on the pipes. Because that's one of the downsides of the recycled water. We've dug up some pipes that have been here 20 years and they had big scale adhesions all over the gate valves. It's just really hard on the piping and it's hard on the cooling towers. So, and then the last little bit is basically they're starting to find all these PFAS in the sewer effluent. And so that's going to kind of require treatment facilities that used to have primary, secondary, tertiary, either to upgrade to RO or have some sort of like PFAS, treatment element in part of it. And so that also kind of like makes it where the recycled water has to go through that treatment because you can't put PFAS on the surfaces outside anymore, like at a golf course. So that recycled water has to become more expensive. So why not just throw in the RO filters and do the whole shebang and charge more altogether? So that's kind of the reality. That's where we kind of see it. But because of that dying of the recycled water, this is my last little pitch, is that you will see more of this do-it-yourself gray water systems. Because now power goes back to the people to small localized treatment systems to either get your lead points or to look at the energy that it goes into maintaining that system. Maybe it benefits you, maybe it doesn't, a little bit like solar. And then the last little thing I wanted to mention that Alex mentioned too is when you do design these gray water systems, you are designing like a mechanical system, and all that piping, all those valves, all those meters to like say capture it down in the mechanical room, push it up, that takes a lot of input, a lot of maintenance, and a lot of oversight. So it's really quick to lose its ROI. It's much better to almost rainwater capture to a large tank and then let it flow gravity out to like some plants. Almost like the Lean Six Sigma kind of concept of if you make this too mechanically complicated, you're going to lose your ROI really quick. So we had some labs that were like that, where we captured the condensate, but then the amount of copper piping, the amount of time it takes to maintain it. And then if a plumber has to go and maintain it, they're not used to seeing that kind of system. And so it seems a lot better almost based on where you're at to almost capture it and then utilize nature to kind of help you find where to divert that item or that water in sort of a less mechanical way. So, but that's it for me. I think that's my pitch. Thank you. That's the recovery condensate. We have a lot of construction going on the last like 10 years. So that's allowed us to kind of build these systems into the buildings because it's really hard to do it later once all the sewer piping's in. And so that's one of the sort of caveats, but that's it for me.
Awesome.
Thank you.
Jeff, thank you so
All right.
much. And
Okay.
and Eli, Alex, and Jeff, these were great kind of windows onto this issue. We got a lot of great comments and questions here in the chat, which I'll get to momentarily. One thing I forgot to mention at the beginning, but I wanted to circle back again for researchers. UC has really got an exceptional environment because you have enormous latitude in stamping your own drawings and kind of approving your own projects. And so, as benefits and curses, it gives you the opportunity for a lot more flexibility and exploration, but also puts a lot more on campus engineering to do some of this work. So I just wanted to point that out to our research community is that UC campuses may be a great crucible of innovation because of the combination of regulatory environment and, as you can tell from these presentations, real eagerness to explore what makes sense. Um, and I would also kind of ask for Alex and Eli and Jeff. Um, have you interacted with any faculty members who do research on water treatment and are using some of these systems on your campuses as part of their kind of research agenda? Eli, probably not because you're all just medical people. But Alex and Jeff, do you have any faculty members who have approached you there?
My answer is pretty quick. We don't really have any faculty doing water reuse, water treatment research on campus.
Okay.
A lot of our faculty is either in geology or on the engineering side, it tends to be computer science and electrical engineering.
Yeah.
But the geology professors are incredibly helpful in guiding our in bringing our groundwater well online. We have some tremendous guidance in terms of how to do that in a way that is defensible. Should we, you know, should it lead to litigation? They say do
Yeah.
this, do that, test for this, test
Great.
for this. This is the frequency. So we do have faculty engagement, just not in water reuse directly.
Very good. Good. Okay, thank you. How about you, Jeff? Any water nerds on campus that you play with?
Yeah, we've had a few. So like an interesting thing I did was we had the School of Engineering and I took some undergrads that needed a project and I took them to the cooling towers. And I said, okay, tell me, this is sort of a nerd out thing, is like in the cooling towers, your water droplet drops from say 80 degrees to 65 and it has like a delta T. And I said, tell me if there's actually a better delta T with using recycled water in the condenser system. And there
Mm.
actually was.
Huh.
And so they made like, it was really cool. Like they made like a little plexiglass cooling tower and then they put thermometers on it with a little fan to scale it down. And then they ran it on potable and saw how basically you had this heat loss. And then they did it with a sample of the condenser water. And the heat loss actually was higher without as much evaporation. And it's kind of funny because like here you are pumping recycled water into these cooling towers and you never ask if it's actually beneficial.
Interesting.
And my theory is that the salt molecules in the recycled water hold the H2O closer together. So when it's releasing heat, it's not releasing a molecule. Like
Interesting.
they're
Well,
more tightly bound.
yeah. Well, the compositional effect is heat capacity is also depress its vaporization curve. So interesting
Yeah,
set of perspective there. That's awesome.
yeah, yeah. We'll get it occasionally but not too much because we don't have like a full sustainability engineering degree.
Yeah,
So they don't come running for me for that. So
I will.
no, okay.
That's right. Well, cool. Well, guys, so I want to open up the floor, and in fact, I noticed that Philippe Daniel had a question. So Jen and Ryan, if you could unmute Philippe, if that's possible. I hope that's possible. I don't know if it's
I think I've been unmuted.
awesome. Philippe,
Hello.
hey, good to see you.
Good to see you, and thank you for the presentation. It's very interesting, and I love the way that each campus is crafting things according to the particularity of our context. My question is this, UC system has these broad sustainability goals, and each campus is seeking to kind of meet these sustainability goals and use this as partially justification for some of the projects. And my question, and I had worked on a project with UCLA to evaluate a reuse facility for their cogen facility. And one of the things that I saw early on is the unit cost for this water were pretty high compared to what they were paying for in terms of their water from the Los Angeles Department of Water and Power. And then I began to think about to what degree, if at UC Merced it would cost, $1,000 per acre foot to create some reuse versus at UCLA it would cost $16,000 per acre foot. To what degree do you seek to meet goals collectively as a system as opposed to each individual campus kind of doing it on its own? And what sort of conversations are occurring UC wide?
I'm gonna also where is she? We had somebody from UCOP earlier on, so I wonder
Well,
if
I
anybody talked
can
about that.
speak to that.
Yeah.
So yeah, I mean, Jeff and Alex are on, as well as I are on the UC-wide water working group, and I serve as co-chair. So basically with water, there's not a lot of strong goals. I would say we have a water reduction goal, which actually expires this year and we need to update. So we're trying to figure out how to do that. And then beyond that, we don't really have, there's no targets regarding recycled water. We sort of have, we've come up with new policy that says, hey, you have to do an evaluation if you have a new project. But really, I would say with like water compared to energy, there has just not been a lot of requirements or aggressive goal setting. So it's something we're trying to work on. But the big challenge, as you can see, is the resources to just do a water project. They tend to be a lot more expensive than in a lower ROI compared to energy projects.
Right. And I guess that goes to the heart of my question is there ways of thinking about the ROI instead of just working at UC Santa Cruz on these particular things at scale, that the sustainability dollar would go further at UCSF or UCLA or UC Merced? Is there any sort of kind of pollutant trading kind of stuff conceptually going
Hmm.
on at kind of more of a UC system-wide basis?
Felipe, I'll add to your question. I think the short answer is no. Nothing is currently in place where we can say, hey, UC Santa Cruz, we're the most water efficient campus, I think, in the nation. Our water use per student could not, it's hard to get much lower than what it is right now. We have the most amazing sustainability team. We have an incredible water meter team. We are on it when it comes to water conservation. And I would love to go to Eli and say, hey, Eli, we have water credits. Would you like them? Because you obviously have other restraints and you need some water credits, we're happy to trade. So that's a really great suggestion. I think it's amazing if we looked at the UC system as a whole rather than individual campuses. But on the flip side, one of the things we struggle with on campus is that we look at each project as its own. The boundaries around the project are very tight, and we say you need to meet the stormwater regulations within the boundary of this particular project. And one of the battles we have right now on campus is to change that paradigm to say we should look at our whole campus. And it doesn't matter if this water were to flow downhill a little bit, as long as it gets treated, as long as it's not causing erosion, as long as it's not, as long as we're benefiting the watershed, we should be satisfied with that. And so that just on campus is a struggle we have. So I hear what you're saying, and I'm thinking we're struggling on campus to expand our mindset. To expand it out even further to all the UCs in the UC system, I think it's definitely a goal we should pursue, but just to keep in mind that we're still stuck with our small boundaries that we create for ourselves on campus. But again, I think it's a great idea. I'd love to see some credit trading when it comes to water conservation.
Mhm.
Yeah, I was also, Alex, your concept is like, well, the campus is watershed. Are we being smart within the campus boundary watershed of where the water goes and how we treat it and when we pick it up? That's a very interesting point.
Yeah,
Um,
and the other thing I'll just add quickly is if we can do better about stormwater management and doing water recycling, and then coupling that with like what do we need to do to manage water so we don't have landslides and
Yeah.
storm water infrastructure failure, and then how can we sort of leverage things that we have to do with recycling water and conserving water.
Yeah. Yeah. I know we're coming to the top of our hour, but I want to kind of ask a question that like I find in general that ROI based solely on cost of water in general really rarely pans out. And you all also describe these more soft ROI issues of sustainability, brand equity, et cetera, et cetera. But Eli, for you in particular, isn't there a lot of value in storing some water on campus in case we have a major earthquake and you then need to access water for a week and it may not be clean as it sits in
Yeah,
the cistern, but you remember San Francisco used to have hundreds of cisterns across the city, historically. Some of them are still used.
They're
So-
not really, SFUC really isn't into their systems anymore, but yeah, so we're required to improve our water storage with our hospital project. And it's one of those things where it's a good idea, but it's really expensive.
Yeah.
So, if we can do sort of what is regulatorily required and then to integrate that with the water recycling, that's ideal, but it's, and that could be sort of a side benefit of this project.
Yeah.
But it's unlikely to happen outside of the regulatory requirements.
Fair enough. Fair enough. All right,
All right.
everybody. Well, listen. Yeah, I'm sorry. Go
I was
ahead.
going to say the only additional add on the water storage is we're now looking at maximizing water storage for fire protection
Right.
purposes,
Mhm.
and that's a huge emerging storage issue that we historically did not look at to the same extent we are now.
Sure.
Yeah.
Sure. Makes sense.
Yeah, like on an interesting thing, we just had a fire pump burnout on a new building and it blew down about 3,000 gallons of water overnight. The pump just started running on its own, but it drained down that fire water tank. Finally, the tank ran dry and then the motor kept going and it burned itself up. This was a new project, but just like that goes $3,000 or 3,000 gallons of potable water.
Yeah, boy.
Yeah.
Oof. Yeah. Well, Eli, Alex, and Jeff, thank you guys so much for sharing your insights, your wisdom, and also your experience on the UC campuses and NAWI community. These three are available to talk to you if you want to reach out. We're going to share the slides, and we have this recording available. And I just say on behalf of NAWI, we will let everybody know as research opportunities continue. But even before then, campuses can be an incredible crucible of innovation. But think practical, think cost, think simple. All those three things are parts of design, not just technology. And maybe our campuses are the frontier of that sort of simple innovation in the future. So from all of us at NAWI, thank you, guests, for coming today. And thank you, audience. And we look forward to seeing you on future NAWI webinars. From all of us at NAWI, thanks very much.
Thank you
Bye-bye,
so
everybody.
much.
All right. Thank you. All right, bye-bye.